Hello, everyone, and welcome to today's lecture on continuity. This is one of the most fundamental concepts in calculus, and I promise you, once you understand it, many other ideas in calculus will start clicking into place. Let me start with a question. Have you ever drawn a curve without lifting your pencil from a paper? If you have, then you've already experienced what in mathematics we call continuity. Today, we're going to make this intuitive idea precise and explore how it applies to different types of functions. So, what does it mean for a function to be continuous at a point? Let me give you a formal definition first, and then we'll break it down. A function f is continuous at a point a if limit of f of x as x approaches a is equal to f of a. Now, I know that it seems simple, maybe even too simple, but there's actually a lot packed into this definition. For this equation to be true, three conditions must be satisfied. First, f of a must be defined, meaning it is in the domain of f. Second, the limit f of x as x approaches a must exist. And the third, the limit must equal the function value. Think of it this way. If you're walking along the graph of a function and you can pass through a point a comma f of a without jumping, breaking, or encountering a hole, then the function is continuous at that point. Let's look at an example to see how it works in practice. Consider the function f of x equals to x squared plus 2x plus 3 at x equals to 1. Is this function continuous at x equals to 1? Let's check our three conditions. First, is f of 1 defined? Yes, we can plug in x equals to 1, and we get f of 1 equals to 1 squared plus 2 times 1 plus 3 equals to 6. Second, does the limit exist? Let's calculate. Limit as x approaches 1 of x squared plus 2x plus 3. Since this is a polynomial, we can use direct substitution, and we get 6. Third, does the limit equal f of 1? Yes, both f of 1 and limit are equal to 6. Therefore, f is continuous at x equals to 1. See how smoothly that worked? That's because polynomials are particularly well-behaved functions. Now let's look at something a bit trickier. Consider g of x equals to x squared minus 4 divided by x minus 2 at x equals to 2. Is g continuous at x equals to 2? Let's check. First, is g of 2 defined? G of 2 equals to 2 squared minus 4 over 2 minus 2. 0 over 0. We're dividing by 0, so g of 2 is not defined. This means g is not continuous at x equals to 2. We don't even need to check the other conditions. If any one condition fails, the function is not continuous at that point. Now, here's something interesting. Even though g is not continuous at x equals to 2, we can still find the limit. Limit of x squared minus 4 divided by x minus 2 as x goes to 2 is equal to limit as x goes to 2 of x plus 2, x minus 2 over x minus 2. We cancel this x minus 2 and we get limit as x goes to 2 of x plus 2 is equal to 4. The limit exists, but since g of 2 is undefined, the function has what we call a removable discontinuity at x equals to 2. We could fix this by defining a new function that equals g of x everywhere except at x equals to 2, where we define it to be 4. Before we move on to different types of functions, let me explain the three main types of discontinuity you'll encounter. First one, removable discontinuity. This occurs when limit of f of x as x goes to a exists, but either f of a is undefined or f of a is not equal to limit of f of x as x goes to a. We call it removable because we can remove the discontinuity by redefining the function at that single point. An example of such a function would be h of x equals to sine of x over x. It has a removable discontinuity at x equals to 0. The limit as x goes to 0 is equal to 1, but h of 0 is undefined. Next one is infinite discontinuity. This occurs when at least one of the one-sided limits is infinite. The function has a vertical asymptote at the point of discontinuity. The example of such a function would be f of x equals to 1 over x or 1 over x squared and so on. This function has an infinite discontinuity at x equals to 0 because limit of 1 over x as x goes to 0 from the right side is equal to positive infinity and from the left side equals to negative infinity. And the third type of discontinuity is jump discontinuity. This occurs when both one-sided limits exist, but they're not equal. For example, limit of f of x as x goes to a from the left side is not equal to the limit of f of x as x goes to a from the right side. The function jumps from one value to another. Consider the step function f of x equals to 1 if x is less than 0 and 2 if x is greater than or equal to 0. At x equals to 0, we have limit from the left side of 0 equals to 1, and limit from the right side of 0 is equal to 2. So there is a jump discontinuity. Understanding these types helps us classify and analyze discontinuities when we encounter them. Now that we understand continuity at a point and types of discontinuity, let's talk about entire families of functions that are continuous. First, polynomials. Here's a wonderful fact. Every polynomial function is continuous at every real number. Why? Because we can always use direct substitution to evaluate limits of polynomials. For instance, f of x equals to 3x to the fourth power minus 2x cubed plus 5x minus 7 is continuous everywhere. No matter what value of a you pick, limit of f of x as x goes to a equals to f of a. What about rational functions? These are functions that we can write as one polynomial divided by another. For example, h of x equals to x squared plus 3x plus 2 over x squared minus 1. Rational functions are continuous everywhere they're defined. The only place where they might not be continuous are where the denominator equals to 0. For h of x, we need to find where x squared minus 1 equals to 0, which gives us x equals to plus minus 1. So h is continuous for all x except where x equals to 1 and negative 1. Now, where is f of x equals to 2x plus 1 over x squared minus 5x plus 6 continuous? First, let's factor the denominator. X squared minus 5x plus 6 equals to x minus 2 times x minus 3. The denominator is 0 when x equals to 2 and x equals to 3. Therefore, f is continuous for all real numbers except x equals to 2 and x equals to 3. Now, root functions require a bit more care. Let me explain why. For odd roots, like cube root, there is no problem. They're defined for all real numbers. The function f of x equals to cube root of x is continuous for all x. But even roots, like square root, are only defined for non-negative numbers. The function f of x equals to square root of x is continuous on interval from 0 to infinity. At x equals to 0, we'd say f of x is continuous from the right side. What about composite functions involving roots? Here's where things get interesting. Where is h of x equals to square root of 4 minus x squared continuous. For h to be defined, we need 4 minus x squared to be greater than or equal to 0, which means that we have 2 minus x, 2 plus x greater than or equal to 0. So x is positive between -2 and 2. Since 4 minus x squared is a polynomial, meaning it's continuous everywhere, and positive on the interval from -2 to 2, and since the square root function is continuous wherever it's defined, h is continuous on an open interval from -2 to 2. At the endpoints, we can check that at x equals to 2, limit as x goes to 2 from the left side of square root of 4 minus x squared equals to 0. And h of 2 equals to 0 as well. So h is continuous from the left side at 2. On the right side, at x equals to -2, limit as x approaches -2 from the right side of 4 minus x squared equals to 0, and h of -2 is also equals to 0. So h is continuous from the right side of the -2. Therefore, h is continuous on a closed interval from -2 to 2. Transcendental functions, exponential, logarithmic, and trigonometric functions are the workforces of calculus. The good news is that they're continuous wherever they're defined. Exponential functions like f of x equals to e to the x, or g of x equals to 2 to the x power are continuous for all real numbers. No breaks, no jumps, just smooth exponential growth or decay. Logarithmic functions like f of x equals to ln of x, or g of x equals to log of x with a base 2 are continuous for all positive real numbers. Remember, we can only take logarithms of positive numbers. Let's look at an example. Where is f of x equals to ln of x minus 3 continuous? We need x minus 3 to be greater than 0. So x should be greater than 3. Therefore, f is continuous on the interval from 3 to infinity. Now, for trigonometric functions, sine, cosine, tangent, and their friends, they are continuous wherever they're defined. Sine and cosine are continuous everywhere. Tangent has a vertical asymptote where cosine of x is equal to 0. So tangent of x is continuous everywhere except x being pi over 2 plus n pi for all integer n. For example, f of x equals to tan x, tangent x, over x squared minus 4. Where is this function continuous? So this function has two potential issues. Tangent of x is undefined at x equals to pi over 2 plus n pi, where n is an integer. And when x squared minus 4 equals to 0, so x is equal to plus minus 2. So f is continuous everywhere except at x equals to plus minus 2 and pi over 2 plus pi n, where n is an integer. Now here's a beautiful theorem. If a function is continuous and one-to-one on an interval, then its inverse function is also continuous. This is why arcsine, arccosine, arctangent, and logarithmic functions, which are inverses of exponential functions, are all continuous on their domains. For example, f of x equals to x cubed is continuous and one-to-one for all real numbers. Therefore, the inverse of the function f inverse of x, which is cube root of x, is also continuous for all real numbers. Similarly, f of x equals to e to the x is continuous and one-to-one on all real numbers. Then its inverse, ln of x, is continuous on its domain from 0 to infinity. So let me leave you with one final example that combines several concepts. Where is f of x equals to square root of ln of x plus 1 continuous? To analyze this, we need to work from inside out. First, x plus 1 must be positive for ln to be defined. So x should be greater than negative 1. Second, ln of x plus 1 must be a non-negative for the square root to be ln of x plus 1 greater than or equal to 0, which means that x plus 1 should be greater than or equal to 1, so x should be greater than or equal to 0. Therefore, f is continuous on the interval from 0 to infinity. Remember, continuity is about functions behaving nicely. No jumps, no breaks, no surprises. As you work with more functions, you'll develop an intuition for spotting where continuity might fail. The key is to look for division by zero, even roots of negative numbers, and logarithms of non-positive numbers.